Hi, thanks, Marcus, and it's good to be involved with this. It's a bit new for us, and I just wanted to take some time to, maybe introduce ourselves to people who aren't aware who Hamamatsu are. Hamamatsu, so who are we, what do we do? So we are a photonics company, so in this sector maybe that's not so clear. So it's anything that uses light or any part of the electromagnetic spectrum for detection, emission, that kind of things. So we're often found inside of other products, and we're probably a bit hidden from, if you're walking around and looking at different machinery, you probably wouldn't see we were there, but we most likely are in some way, shape or form. So we've been going around 70 years now, and we have well over 5,000 employees around the world working on all sorts of different applications, from medical to automotive, and of course I'm here to discuss what we're doing in the printing space. So primarily we're based in Japan, in Hamamatsu City, that's where the name of the company comes from, but we have major offices all around the world for sales support and other things like that. So photonics, what is it and how can we use it in the printing market? So there's a number of ways we can help a printing process with photonics applications. So for example, at the very start of a printing process, when you want to remove static when it's going in, rather than using something like corona discharge, you can use soft X-rays. So soft X-rays can completely neutralize the charge going into a system without damaging any of the substrate beneath it. Then, as you go further into it and you start depositing ink and other materials, then we have UV, which is a very standard way of curing in the system now, and also that you can electron beam cure for those applications in packaging where you want minimal or no migration at all. Whilst you're doing these, you can monitor these systems by using simple diodes and other detection systems which can monitor how effective this is being, how much power you're getting down to your substrate at different parts of it, and this can be used to monitor and test as you go through the lifetime of your systems. Before you do a final cure, so usually you pin with a lower power UV lamp, before you go and deep cure it and final cure it, you can use even lower UV light, so somewhere between 172 and 222 nanometers usually, for surface modification. Now, from our experience, this has primarily been used for matting surfaces, so for wood printing, for example, then to get a matte finish and remove some of the gloss from there. So for that, we would use an X-timer light source. And again, you can use a UV power meter to monitor this and control this kind of system. And then at the very end, as you're rolling up your final product, then you can again use another soft X-ray system to completely neutralize the charge and make sure you get no charge build-up, sticking, that kind of thing. In addition, then for 3D printing, additive manufacture, that kind of thing, then we have been working very closely with some customers to develop very flexible UV light sources, which are designed to just follow the inkjet nozzle so that you cure almost immediately after it deposits, so it has no chance of spreading or deforming or anything like that. So as with all of you, I imagine, then we've been working with UV LEDs specifically for 15, 20 years, and the market has developed considerably, certainly in the last 5 years. And so we started off with much bigger, bulkier systems, and now a lot of our systems are designed to daisy chain and basically be as wide or as narrow as you need them to be. So what are the things that we have to consider when we're designing these systems, and what things do we need to perhaps discuss with ink manufacturers, printer manufacturers at the stages where we're not so much involved? Then there are some things that we don't control on our side, and that's stuff like the ink formulation and deposition, which is usually controlled by the printer manufacturer or the end user, depending on what they decide to do. The print speed, then of course that is a limitation of whatever components you choose within there, but also if a customer has a target speed, how do we help them achieve that with our developments? And then finally, the substrate, is it wood, is it corrugated, paper? Is it, just normal paper, plastic, whatever it may be? Then all of these will have a different effect of how effective our systems are at helping them. So on our side, then we can make developments on the wavelengths, the window size, so the dose of the system, how the optics themselves within the LEDs are managed to be able to focus the light and make sure that the maximum amount of power is output in a uniform way so that you don't get any non-uniformities or issues within the print itself. And also with temperature control, so this is something that I'll go into later, but it's a common issue we had in a last iteration of products, which we've done some development on moving forward. So the wavelength. So as in the past, then people used arc lamps. These have a wider wavelength range, which means in terms of your ink formulation and things like that, then you don't need to be as tight because you have quite a wide band of wavelengths at which it can cure. With an LED, then you're looking at a 5 to 10 nanometer bandwidth at most, and even then the peak is going to be much narrower than that. Now this can cause some problems for some applications due to the photoinitiators that are needed to print these. So typically on the market you'll see them between 365 and 405 nanometers. This is partially because of the cost of these LEDs in this system, but also the power that they can output. Once you start going to lower wavelengths, then the cost of LEDs can go up quite dramatically. And obviously, if you're manufacturing a system, you want to make sure that it's as cost effective as possible so that you can maximize profit and things like that. However, certainly in the last 12 months, we've seen much more interest in lower wavelength applications. So we've recently developed a 280 nanometer UV LED unit for R&D purposes, with the plan to further develop this once it's been tested at printer manufacturers, ink manufacturers, to see if it actually gives the benefits that we hope it can. This is particularly for whites and clears. Again, going back to the photo initiator issue, and if we can reduce the photo initiators in the product by using a lower wavelength to help the higher wavelength cure the entire bulk, then we can reduce the need for those photo initiators and perhaps open up some new packaging applications to some of our customers. And also, the secondary application for this is to reduce some surface tacking. Now, some of this has been largely solved by ink formulators, but for some applications there are still problems with surface tacking, so the stickiness of the ink when it is deposited. So, for many years, then there was a bit of an arms race between lots of different UV LED companies, and it was, how powerful can we make these LEDs? And this was, in the infancy, I suppose, of these kind of technologies where we needed a certain power output to successfully cure. Now, in the last 4 or 5 years, it's probably switched more to dose, so the amount of UV that is reaching your substrate. So this can be changed on our side. We can either increase the LED power or we can increase the window size to accommodate this dose increase. However, this can often lead to temperature and cooling issues because the more LEDs you have, the more you have to cool it either with water or air cooling. And also a lot of people in the market now are using higher level LEDs but running them at maybe 50-60% capacity. This means you can run it for a much longer lifetime than maybe the specification sheet would normally say. So instead of 20,000 hours, maybe it's 30, 40, 50,000 hours at this. Whereas if you ran one at 100%, you'd have to change that unit much quicker. So as I mentioned, as you increase the power and you increase the window size of these, then we found actually there was some problems with temperature control. Certainly because we use air cooling, you can use water cooling, but obviously you then have extra components to add to your system, and it's a much more involved installation. With our air-cooled systems, then the idea is you can daisy chain them so they can be 100 mil wide, they can be 1 meter, 2 meters wide. It's entirely up to you. But what we found from our customers was that with a lot of these, at the boundary between two units, you've got conduction and convection buildup. So you've got big heat buildup at the sides. which built up the heat in the LEDs at these sides, and then you've got non-uniformity across the front of the print. So our guys in Japan spent a long time working with customers to further develop this, and developed what they're calling the Thomas system. So with this system, then we have built a dual wall insulation into the device. And what that means is at the extremities of the UV LED unit, there is only cold air. The cold air is then pushed down the sides of the unit, and then the hot air is vented out through the center. This means at no point is there hot water touching the extremities, and it means where you get these daisy chain operations, then we've eliminated that issue completely. In addition to that, we also customize the heat sink. So at the moment, that is just to improve the efficiency of this particular line of products, but in the future, we expect that will allow us to reduce the size considerably moving forwards. In addition to that, then, I mentioned surface tacking earlier, then one way of getting rid of surface tacking is nitrogen inerting. Now, if you're using nitrogen in anything, then usually you need a big housing around your entire system, entire unit, but then you need a lot of nitrogen to fill that and make sure that's a completely inert environment. We had some customers who didn't have the space to do that, particularly in smaller inkjet presses. So to combat that, we have developed the HANS system, which is basically only covers the front LED window with the nitrogen, so it completely inerts. So to do this, then the front part, the purge block, is tapered, so it accelerates a small amount of nitrogen across the front of the LED window. And this has two effects. So it inerts and it limits the oxygen inhibition, but in addition, it also prevents any particulates from earlier in the printing press from moving under that LED window and curing, contaminating, etc. Then we have the two assist blocks at the side that guide it across the window, and at the other side we have what we call the assist block, but basically that just removes the nitrogen at the other side. So you only have this small area in front of the LED window that is covered with nitrogen. So they're just a couple of ideas of the challenges that we've come across with our customers. Now, as a few people have said already this morning, we feel it's very important to collaborate and discuss future developments with both ink manufacturers and OEMs moving forwards. So I will be here for 2 days, and we've got a little stand out there. So if you've got any questions, or if you just want to discuss, anything about what you're looking to do, then I'll be happy to talk to you. Thank you.
Thank you.